short wavelength gamma rays with wavelengths of down to 10 to the 14, 10 to the 15 meters and below, except below that are very hard to produce, through the X-ray spectrum that runs from wavelengths of about 10 to the minus 9 to 10 to the minus 12 meters, and then the ultraviolet light, which is the chunk of the spectrum immediately beyond the deep violet light at 400 nanometers, that is the shortest wavelength our eyes can see. And then on the other side, to the left of the red light, we have infrared light, and below that, microwaves and radio waves, whose wavelengths can be hundreds of meters. And so there's this entire spectrum, and in fact, we're familiar with it, we use it. Our eyes are sensitive only to this tiny little bit of the electromagnetic spectrum. Our eyes have all kinds of inefficiencies, but in this case, our eyes are well adapted to where we live. If you look down here at the bottom of this plot, this is the transparency of the atmosphere, and you see that, for example, gamma rays and X-rays are not very useful, despite Superman claim to the contrary. X-ray vision is not very useful because X-rays are very quickly absorbed in the atmosphere. They do not penetrate. Visible light penetrates the atmosphere. A little window in the infrared penetrates the atmosphere. And then radio waves penetrate the atmosphere. Well, we know that because that's how we watch TV. But the wavelengths of radio waves are too long. You would need your eyes to be antenna. They would need to be on the order of meters in size. We do not have eyes meters in size. There would also be other limitations. It would be hard to see features of the universe smaller than a few meters across. So, given our need for fine resolution, our eyes are well adapted to the conditions under which we evolved. But the universe, on the other hand, produces light across the entire spectrum, from high-energy gamma rays to radio waves, and it's important, in order to collect information about the universe, to be able to observe it in all possible frequency bands. And indeed, with technology, people have developed ways to observe the universe in all of these frequencies, and at every time that we've developed a new technology and a new way to look at the universe, there have been new and often surprising discoveries made. Note that observations in many of these bands, in the ultraviolet, in X-rays, and in gamma rays, for example, need to be made outside the atmosphere. Putting a very good gamma ray detector on the ground will not buy you anything because gamma rays from space will not penetrate. So these observatories, including actually infrared observatories, tend to be space-borne, or at least high-altitude balloon flights. Radio telescopes can be placed on, are placed on the ground. Those are these very large dishes that receive radio waves, and over the course of the class we will have occasion to use information collected by all of these bands. So it's the richness of the spectrum corresponds to the richness of phenomena out there. We're almost done with our discussion. One last statement now that we have our understanding of the spectrum. A hot object radiates. That's what we discussed. Everything radiates, as long as it's warmer than the surroundings. For a dense, dark object, so for an object that essentially absorbs light that hits it, such as you, me, the Earth, and it turns out the sun, the radiation is almost completely characterized, and it's precisely completely characterized for some idealized black body, an object that absorbs any light that falls upon it, by the temperature. It turns out that the nature of the radiation produced by a warm object, if it's dense, is essentially a property of light and thermodynamics and has nothing to do with the object itself. And this is called blackbody radiation, and it has two important properties. One is that hotter objects are blue. This despite the fact that blue is a cold color and red a warm color to our intuition. It turns out that hotter objects radiate shorter wavelength. In other words, a blue glow is hotter than a red glow because a red glow has a longer wavelength. This is summarized in Wien's displacement law, which says that the wavelength at which an object emits more radiation than any other wavelength, the wavelength of maximum emission, multiplied by the object's temperature is actually a constant, so that if you double the temperature of an object, the wavelength at which it emits is halved, and Wien's constant is written over here. It's got units of meters times Kelvin, so wavelength times degree. The other and more familiar statement is that hotter objects produce more light. This is encoded in the Stefan Boltzmann relation, which tells us that the rate at which each meter squared of an object radiates, of course a big object radiates more than a little object if they're the same temperature. 2 light bulbs make more light than 1 light bulb. So we need to normalize to the rate at which an object produces radiation per meter squared, that's F, in watts per meter squared, and the rate at which each meter squared of an object radiates is proportional to the 4th power of the temperature in degrees Kelvin, and so doubling the temperature leads to a 16-fold increase in radiation, and the constant, the Stefan Boltzmann constant, sigma, has this numerical value in our units, and its units are watts per meter squared per degree Kelvin to the 4th. Let's take a look at what this black body radiation looks like. Here we have a plot of the relative intensity in various wavelengths as a function of the wavelength from near zero to a few times 10 to the minus 6 micrometers, and so the visible band is located over here, and the black body curve has this characteristic shape. As I said, it's independent of the material, and the curve I've plotted here is the curve for an object that glows that has a temperature of about 3,000 degrees Kelvin. 3,000 degrees Kelvin is about the temperature of the filament in an incandescent light bulb. And what you will notice is that most of the light produced by an incandescent light bulb's blackbody radiation is in fact not